Welcome to Brain Vision.
Relate the energy at A, and this is going to be equal to the total mechanical energy at C. We can then say that the potential energy at A equals the potential energy at C plus the kinetic energy at C, and this would be equaling the potential energy at C plus the kinetic energy at C for the center of mass plus the kinetic energy at C, the rotational kinetic energy at C. So we can say mgr equaling mg times r minus r cosine of theta. R would be the radius of the curve, and then lowercase r would be the radius of the actual sphere. This would be 1 plus times the mass velocity at c squared plus 1/2 times the moment of inertia times the angular velocity sub c squared. We know that mgr is equaling mg radius of the curve minus the radius of the curve minus the radius of the sphere cosine of theta, close parentheses, plus again 1/2 mv sub c squared plus 1/2 times the moment of inertia of a sphere, 2/5 mr initial squared multiplied by the velocity at c divided by the radius of the sphere, quantity squared. And so we find that the velocity at c for part A is equaling square root of 10/7 multiplied by g times r, the radius of the curve, minus the radius of the sphere, cosine of theta. Extend the square root. This is equaling the square root, again, of 10/7 multiplied by 9.8 meters per second squared multiplied by 0.245 meters times cosine of 45 degrees. Let's extend the square root, and v sub c is equaling 1.56 meters per second. This would be our final answer for part A. For part B, it's asking us essentially, what is this length d? And so we can say that the initial location of the ball, x initial, equaling the radius of the curve minus the radius of the sphere times sine of 45 degrees, and y initial of the ball is equaling r, the radius of the curve minus the radius of the curve minus the radius of the sphere, cosine of 45 degrees. We know that the initial velocity in the x direction would be equaling v sub c cosine of 45 degrees, and the initial velocity in the y direction would be equal to v sub c times sine of 45 degrees. So we can find the time that is in the air. We can say here that y final equals y initial plus vy initial t plus 1/2 at squared. This essentially becomes, this will equal the radius of the curve minus the radius of the curve minus the radius of the sphere times cosine of 45 degrees plus the velocity sub c sine of 45 degrees times t minus 1/2 gt squared. This essentially becomes 4.90 t squared minus 1.101 t minus 0.07178 equaling 0, knowing that y final is at the ground, or 0 meters. And so t, the only positive root for t would be 0.277 seconds. And so we can say that d, the distance from the base, would be equaling x. This would be equaling the x initial plus v, x initial times t. This is equaling r radius of the curve minus the radius of the sphere times sine of 45 degrees plus the velocity sub c times cosine of 45 degrees times t, and we can solve. So for part B, d is equaling 0.245 meters times sine of 45 degrees plus 1.557 meters per second. We can cancel out we can rather round at the very end, times cosine of 45 degrees multiplied by 0.277 seconds, and we find that d is equaling 0.478 meters. This would be our answer from the distance between where the ball lands and the base of the curve for part B. That is the end of the solution. Thank you for watching.